All right, welcome to this big video on graphing. October is going to be very fun. I just know it. Now in this video, we're going to start by making an observation about local behavior of vertical asymptotes. Okay, so we're going to start by looking at Desmos and see if we can generate some sort of generalization. And then after that, we're going to get into the actual graphing. Okay. Let's see if she lets me record this video. All right, so let's tab over real quick and look at this function. Let's look at the function 1000, go big or go home, divided by x plus 1 times x minus 5 squared times x plus 5 cubed. And so, we know some things about these functions now. We know the end behavior. We know that there are vertical asymptotes at -1, 5, and -5. Okay? And so specifically, and we know they're not removable discontinuities because the factor is not shared in the top. Right? If I added an x plus 1 in the top, there'd no longer be an asymptote at -1. It's a removable discontinuity now. So we're trying to say, kind of generalize what we know about zeros and multiplicities of polynomials to talk about vertical asymptotes here. So let's look at this asymptote right here. This asymptote is at x equals 1. It goes to -infinity on the left and +infinity on the right. Now what if we change that one to a squared? Look at, focus in specifically here. I'll actually show you where to focus in. Focus in on this orange, not that orange line. Focus in on this orange line and look at how the vertical asymptote changes if I make this exponent a squared. Only look at that vertical asymptote. If I square it, now they're both going positive. If I cube it, opposite directions. To the fourth, same directions. Fifth, opposite directions. Sixth, same directions. All right, and in general, right, look at these other ones as well. X minus 5, that's going in the same direction on each side of the asymptote because x minus 5 squared. X plus 5 cubed, going in opposite directions on either side of the asymptote. Okay? So if the exponent, if the multiplicity of that 0 in the denominator is odd, they'll go in opposite directions. And if it's even, they go in the same direction. Okay? We're going to use that observation when we graph things. Okay? So if the factor in the denominator has odd multiplicity, then the function goes in opposite directions by the vertical asymptote. Right? So kind of like 1 over x. And similarly, if the factor in the denominator has an even multiplicity, then the function goes in the same direction by the vertical asymptote, like 1 over x squared. So notice how we're talking about multiplicities again. And just like when we talked about multiplicities for polynomials, I said locally, if it's even, it behaves like x squared. If it's odd, it behaves like x or x cubed. Well, here it's the same idea with these multiplicities, right? Locally, if we're only looking around that vertical asymptote, it's going to behave like 1 over x or -1 over x or 1 over x squared as well. So it all ties in together. There's the multiplicities popping back in 5.6, just like they were in 5.3, which is kind of cool. All right. So when I ask you to graph, of course, you can use Desmos to check your answer. But when I'm asking you to graph, There are three things that I want you to include clearly in your graph for rationals. Okay? Things to include on your rational graphs. That looks like vational, which actually sounded not like I thought it was going to sound when I said that out loud. Include the intercepts and the multiplicities, just like 5.3. All right, if there's an x-intercept with a multiplicity of 2, it should bounce off the axis right there. All right. Include the vertical asymptotes and removable discontinuities. And their local behavior, just like we talked about for those vertical asymptotes. And lastly, do either the horizontal asymptotes or slant asymptotes. I think it's always one or the other for irrationals. Trying to remember off the top of my head. All right, these are all the only things you have to include. It's kind of a lot, but if I say it's the only thing that you have to do, it sounds a little better, right? All right, let's do example 6. Sketch a graph of f of x. Oh, whoa, I have no equal sign. Equals x plus 2, x minus 3, divided by x plus 1 squared, x minus 2. And again, it doesn't have to be a perfect graph. It just has to include the information that we just mentioned. So, step by step, what are the intercepts and the multiplicities of those x-intercepts? Let's find them out. Well, let's start with the x-intercepts. Right, the x-intercepts are when y equals 0. And remember that that's going to be when the numerator is equal to 0 with the same logic we did in that intercepts video. That's going to be when x is equal to -2 and +3. Make sure these are in the domain. Make sure these are not removable discontinuities. So -2 is right here. +3 is right here. Those are our x-intercepts. Similarly, find the y-intercept. That's when x equals 0. It's going to be 2 times -3 times 1 squared times -2. That's going to be -6 over -2, +3. To be the y-intercept. And include information about the multiplicity. So each one of these multiplicities for these zeros are 1. Right? Look at those exponents of those factors. We don't write the exponent because it's a 1. So we know it's either going to cross like this or cross like this. It crosses like a line, multiplicity of 1. Multiplicity of 2 would look like this or this. Multiplicity of 3 would look like this or this. Remember back to 5.3. All right, so we'll incorporate those multiplicities, but we need some more information before we can connect the dots. We need vertical asymptotes and the local behavior and removable discontinuities. So the candidates for the discontinuities, right? The discontinuities are going to be when the denominator equals 0. Discontinuities are going to be right here. -1 and +2. Question is, are these removable discontinuities or vertical asymptotes? Look at the earlier video. They don't share any factors, so they have to both be vertical asymptotes. So at -1, there's a vertical asymptote. At +2, there's a vertical asymptote. And we're curious about the local behavior at the vertical asymptote. So this, right, has multiplicity 2. Because there's an exponent of 2 right here. Which means it's going to go in the same direction. We're going to use that information. This is multiplicity 1. So on either side of this asymptote, they're going to go in opposite directions. Can include that as well. All right. We also need horizontal asymptotes or slant asymptotes. We're curious about the end behavior. Now the end behavior here is a little harder because it's not written out in general form of those polynomials. Okay. So we're going to look at the degree of the top and the degree of the bottom. What's the degree of this top polynomial? That's just a quadratic. And the degree of the bottom? That's something squared times a line. The degree of the bottom is 3. The leading term of the top is x squared. The leading term of the bottom is x cubed. The end behavior is like the end behavior of x squared over x cubed. The end behavior is like 1 over x. So now we know a lot of things. The end behavior is like 1 over x, so our end behavior here is going to look like this. And now we can start incorporating all the directions. All right, that tells us that on the right, oh, and the horizontal, wait. Hold up. Yeah, the horizontal asymptote is eventually at 0. Eventually it's at 0, but it's still able to cross at the X-intercepts. All right. So all that's left is to kind of figure out where this function's positive and where this function's negative. And you can logic your way through this, or you can kind of check with Desmos. But if you just like you can do it kind of either way. And I'm not going to talk too much about doing it by hand here. So let's just kind of write this down. We're going to get x plus 2 times x minus 3 divided by x plus 1 squared, x minus 2. All right, and this should have all the information that we were talking about. The intercepts are all right there. The asymptotes should all be right there as well. Another one at x equals 2. Good, and then this just kind of tells us the shape. We have all the right information. Let's just connect the dots. The shape on the right is, it starts at the bottom, then it goes a little bit over, and then approaches like so from above. Shape in the middle is kind of like a weird little quadratic. And the shape on the left starts on the top and then approaches from below. Again, it gets very close to these intercepts. Okay? And that's how we can sketch a graph, including the relevant information. It's very good to figure out all of this by hand. And then once you have that, you can get like the kind of shape and like the directions, which can be possible to do by hand as well by plugging in some points. But you can just use Desmos for that final connecting the dots. All right, but that's kind of the logic or the step-by-step process that I want you to go for in these ones. But you should be able to know how to look at a graph on Desmos and copy the relevant information over here. And it's good to be able to do it by hand as well. Let me know if you have any questions about this or my expectations for you, but otherwise, have a good one.